So in the last video, we wrote down D'Alembert's principle, and I promise that next time I will derive equations of motion involving the generalized coordinates, okay? And that's what we are going to do now. So let's remind ourselves what the D'Alembert principle is, and from there we'll start changing the coordinates from R to Q, R being the Cartesian and Q are our generalized coordinates. So my relation was mi ri double dot minus fi and dotted with the virtual displacements, okay, and if you sum over all the particles, this is 0, okay. That's your D'Alembert principle, okay. Now instead of the Cartesian coordinates r, I will convert everything to the generalized coordinates, and here is the relation. So I have ri, okay, they are function of all the coordinates q's, and they are 3n minus k, where k are the total number of independent constraints. And we have already assumed that we have holonomic constraints, okay. That's good. Now I can take a differential of this and write dri. I should put vector symbols here, okay. Dri is what? Del ri over del q, let me call alpha, I'm using alpha, okay, dq alpha, and I should sum over all the generalized coordinates, and I will also have a time derivative term, which means I missed writing in the previous line something, so here we should include time as well. Put a comma and make it a t, okay, this is time, t, okay, and dt is missing. Perfect. Now if I want to write down the derivatives, then I should write down ri dot, okay, I'm dividing everything by the time, dt, delta ri over delta q alpha dot, so this dq alpha divided over dt becomes q alpha dot, and you still have a sum over alpha plus delta ri over delta t. Good. And what will the virtual displacement satisfy? Virtual displacements would satisfy delta ri, sorry, that's correct, delta ri equals delta r delta q alpha, okay. As you remember, I have to drop the dt term. That is good. Now before I proceed further, I should state two results which we are going to use in massaging the D'Alembert principle written here, and those two results are the following. Result result, result 1, and the result 1 is that if you take delta ri delta q alpha, and if you put dots both on ri and q alpha, then this equals that relation. So if I can take this and put dots on both ri and q alpha, so delta r I dot over delta q alpha dots. That is result number 1 that we are going to use, and then let's look at result number 2. res ULT, which says if you take delta Ri or delta Q alpha and you put a dot on this, then this is same as delta Ri alpha with a total time derivative. That is correct. Very good. That's correct. So I'm going to utilize these two results. Okay. Now let's look at. Okay, maybe first I should prove them. Okay, that will be better. So let's go here. First one is quite trivial. You see this one. This one is easy. This I can see from here. So you take Ri dot. Okay. And this relation is a linear combination of, is a linear sum of Q alphas. Okay, so this is del Ri over del Q1 dot plus del Ri over del Q2 dot and so forth. And this piece is a function of Q. And Q dot dependence is only here. So if I take a partial derivative with respect to Q alpha dot, only this piece will survive. This will drop out because there is no Q dot in here. So first one is quite trivial, as you can see. Nevertheless, I think I want to do it for you. Okay. So let's do that. I wish I knew how to copy this. Let's see. Is there a way to copy the frame? No. Okay, anyhow. So what I wrote was Ri dot right, that is what we had on the previous slide. Let's check, and you have a summation over alpha. That is correct. Okay. Now I want to take a derivative with respect to Q alpha. So that's what I do. Alpha. Now if I do so, I should not use the same alpha here, okay, because this is dummy, this is summed over. So it makes no sense to keep alpha there. So let's use some other symbol, let's say S, to denote the sum. So this will become del over del Q alpha summation over S delta R. Okay, that's the first term. So I've changed the dummy index alpha to S. Okay, and this term will go away because this does not involve, I'm sorry, there was a Q alpha dot here, and this does not involve a Q alpha dot. Now this is summation over S. I can take this partial derivative and pull through the summation, and it will not act on this because this is a function of Q's and not alpha, so it goes directly to act on this one. So I get del Ri del Q S, okay, and del Q S alpha dot. Okay, this is the right way of doing it. So sometimes student will just read from here that, oh, I'm taking derivative with respect to Q alpha dot, and this is what will be left over, which is correct answer, but you should know how to proceed. I mean, how you should get it. Otherwise, there is chances that you will start making mistakes elsewhere. Now look at this piece. What is this? So delta Q S dot over delta Q alpha dot is, what's your understanding? See, when S and alpha are same, then the answer is 1. Okay, so delta qs dot over delta qs dot is 1. And when S and alpha are different, the answer is 0, because these are independent variables. Okay, so clearly unless S and alpha are same, the answer is 0. And when S and alpha are same, if S and alpha are not same, the answer is 0. And if S and alpha are same, the answer is 1. And that's what a Kronecker delta is. Okay, so this thing is delta S alpha. Okay, so I substitute this thing here, and I get OS delta S alpha. Now what is that? So here there is a sum over S, and unless S and alpha are equal, it always gives 0. So it multiplies 0 to this, so it gives a 0 contribution. And only when this S hits alpha, this gives a non-zero contribution, this entire thing, because this is 1 then, and the result will be delta Ri alpha. Okay, so that's how you show this simple result. So anyway, we have proved our result number 1, which was quite trivial. I just spent some time in showing you the algebra explicitly, but the proof was fairly trivial. Now let me prove the result number 2. Okay, what I want to show is, so I start with the right hand side here in the result 2. Okay, so del Ri dot over del Q alpha. So I start with del R delta Q alpha. Now I will write this as Q alpha, and I will just write down what Ri dot is, and you know what that is. I should use a symbol, different symbol. So it should be delta R. No, not dot. Delta Ri over delta QS dot plus delta R. Correct. That is absolutely correct. Okay. Now you see this partial derivative, I can pull through the sigma, of course, and it will act only this part, because QS dot is independent of QS, so it doesn't work on this one. So it will work on this, and the QS will also go through the delta over delta T and work on this one. Okay. So when I take this and put it here, because the delta Q alpha and delta QS I can interchange. Okay, I can do the interchange. They are independent coordinates for different alpha and different S, and when they are the same, it anyway doesn't matter which order way you write. So the upshot is that I can write this as summation over S delta over delta QS delta QS dot plus over delta T delta Q alpha, right? And that's what the expression for a total time derivative is, del over del T and differentials with respect to coordinate times the velocities. Okay, so this is nothing but d over dt del R. Why I'm putting a dots here? Okay, QED, that's correct, proved. Del R, let me check. Perfect, that's perfect. Okay, so we will utilize these two results in dealing with our D'Alembert principle. So let's proceed then. Now here in this there are two pieces. So first term is this, which includes the dot dri as well, and this is the second term, fi dot dri. Okay, so let's look at the second term first, fi dot delta ri. There is a minus sign as well. So second term was minus summation over all the particles. We had fi dot delta ri. That is correct. Okay, which is same as minus summation over I f I dot delta ri is del ri over del q alpha dq alpha, delta q alpha. Okay, these are virtual displacements, that's why the time part is gone. Okay, now look at this. I can define something called a generalized force. So this part I will call q alpha. You see the index I is summed over, so that's not a free index. Only the alpha index is free. So I define this quantity to be q alpha. So q alpha is summation over I okay, that's the definition of q alpha. And with that, the second term becomes minus q alpha delta q alpha. And it's quite natural to call q alphas to be the generalized forces. You see, here the forces were multiplying the virtual displacements. Here you again have virtual displacements, but those of generalized coordinates. So whatever here is you will call generalized force. Okay, and note that the fi dot delta ri is the work done under virtual displacement, and so is q alpha times delta q alpha. That's also the work done under virtual displacements. Okay, so we have written down the second term in D'Alembert principle in this manner. Now let's look at the first term, which was here, mi ri double dot delta ri. Okay, so that's what we want to write now. So let's see, term number 1, here was term number 2, mi. Now this is going to be very interesting. We are almost there. Mi ri double dot delta ri summation over all I. That's correct. Now this thing I will write as mi. Again for delta ri I will do what I did here. I will write dot delta r q q alpha. That is fine. Okay, this is perfectly that's good, everything is okay. Now I think I can leave around the okay, there is also a sum over alpha now because I am summing over alpha here. Okay, so what I'll do is I'll just pick up this piece and leave the delta q for the moment and just work on this part. Okay, so let's take this. This is, I will leave some space here, or maybe I should go to Okay. So I have mi double dot. Okay, let me go there. mi ri double dot, and then we had del ri or del q alpha. Okay. So what we can do is, I will write this in the following form. See, r double dot involves two time derivatives. So I'm going to pull out one time derivative and leave the velocity, that is r dot, behind. So I write this as d over dt. Even in fact, I should have left behind the mi's also. So let's leave mi also. No, that's fine. Okay, it's okay. So what I do is d over dt mi ri dot q alpha. What is this? Now this will give you r double dot term, but it will generate extra term that I will subtract out. So it will have mi ri dot d over dt acting on this piece, right? That is what is getting generated extra from the first term, alpha. That is nice. Okay, now this is the place where I want to utilize those two results which I showed you. You remember the first one I can use in here. First one was that the time derivative of ri with q alpha I can replace by a time, sorry, not time derivative. The partial derivatives of ri with q alpha I can replace by a partial derivative of ri dot with q alpha dot, right? Let's see here. Okay, ri q alpha turn to ri dot q alpha dot. That's what I will do here. Equals d over dt mi ri dot and del ri dot over del q alpha dot. You'll realize soon why all this is going to be useful. Minus, in the second term I'll use the second result. And what was that? If you take a time derivative of this quantity, you can replace it by putting a dot over ri, right? So that's what I'll do. Minus mi ri dot del ri dot over del q alpha. That's good, and it is good because of the following reason. This I can write as d over dt of, now what is this? This is, I can put the ri dot in here, inside the derivative term here. So it will become ri dot square. But then I will have an extra factor of 2, right? Because if you take the derivative of r dot square, it gives 2 r dot del r dot. So I get an extra piece of 2. So I remove that one by writing half and then del ri dot square over q alpha dot minus the same thing here, half mi del over del q alpha ri dot square. Okay, now these half mi pieces, these pieces, I can put them next to the ri dot squares, same in both. And you know that half m ri dot square is the kinetic energy of the ith particle. So this will become d over dt half del over del q alpha dot half mi ri dot square, right? Minus again del over del q alpha and mi ri dot square, and there's a half. These are your kinetic energy terms. Okay, now if you go back and see here, in the term, that was the term number 1, so I substitute here. You see, this is what this is the thing which I have calculated. So I plug it in here. What is this? This is summation over alpha, and I'm bringing in the summation over I. And what is that? D over dt, del over del q alpha dot here, and then you have summation over all the kinetic energies of individual particles, and that will give you the sum of the kinetic energy of the entire that will give you the kinetic energy of the entire system. So that's what we get here. Here d over dt del over del q alpha dot times t. Okay, see again carefully, d over dt del over del q alpha dot, and the sigma I, this thing is the total kinetic energy of the system, which I denote by T. That is good. And then you again have one more term, summation over alpha del over del q alpha T. Check it again. This is del over del q alpha, the minus sign here, and T, summation over all the particles. So that's the total kinetic energy of the system. Okay, that's nice. Now if I combine the term 1 and 2, I get the D'Alembert principle in the following form. So I get summation over alpha d over dt del t over del q alpha dot minus del t over del q alpha, and all this, remember, was dotted with the q alpha. This is equal to 0. Right? So that's the form of D'Alembert principle in generalized coordinates. And this is very nice. One, already when we wrote down the D'Alembert principle, the constant forces were gone. But now what we have achieved is, we have written down a relation which involves only independent variations of generalized coordinates. Remember, we were using holonomic constraints. So now I can put the coefficient of q alpha to be 0 for each alpha, right? Because this sum is 0, but because the variations delta q alpha are all independent of each other, this can hold true only if the individual coefficients also vanish. So from here, I get my desired result, d over dt delta t over delta q alpha dot. Okay, I think I went a little fast. I have included only the second term. The first term I have missed here. So let me just write it down here. Minus, you remember, this is what you get from the first term. Okay, and then whatever I said just now about independent variations and being able to pick out this coefficient to be 0, which they are correct, and I get my final result to be d over dt del t over del q alpha dot minus del t over del q alpha equals q alpha. This is nice. This is very nice. This is nice for several reasons. Okay, this is the equation of motion that the system has to satisfy. Okay, each coordinate q alpha will evolve according to these set of differential equations. These are not all I mean, they are not necessarily uncoupled, they are all coupled equations, but that's what you have. And look at the t in the numerator in these derivatives, they pertain to the entire system. It's not the kinetic energy of individual particles which is entering, it's the kinetic energy of the entire system as a whole that is entering in here. And if you look at the q alpha, okay, that's also, you see here, why it's not working, yeah, here. When you're looking at q alpha, there is a summation over all the particles already in there. So it's also something not about individual particles, but the system as a whole which is entering the equation. Okay, so somehow these equations are sensitive to what the system is doing as a whole, and is not so much caring about what individual particles are doing. Okay, so from there we will be able to have a full description of our system by solving these equations. Now what I will do in the next video is write down this in slightly different form. What I'll do is I'll take the Q alpha, the generalized forces, and write down using potential. So what I will say is, let's say the forces can be described by scalar potentials, and then I will rewrite this equation in a slightly different form, which is generally more used. But nevertheless, this is the equation, and this we will call as several such sets I will call as Euler Lagrange equations. So this is Euler Lagrange equation. Okay, so we have done a lot of hard work in arriving at this result, and that's quite nice. This will be almost our starting point now, except for the fact that I have to do a little bit for something for the Q alpha. Okay, see you then in the next video.